Hello, everyone. Welcome to the Best Data Community Summit 2021. I want to start by actually thanking Red Hat and all the partners for making sure that we still have a PASS Summit this year, albeit it's online. My name is Pedro Lopes. I'm a principal architect in the Azure Data Group, and I am nowadays the release manager for SQL Server 2022, which you've heard today from Bob Ward about the major highlights of our investments there. And I have the pleasure of actually having Bob and Joe Sack answering all your questions in this session today, because I won't be, I don't have the real estate to look at the chat right now, but you're in very good hands. So without further ado, this is what we're going to discuss today. First, we'll start with Query Store. And again, Bob has mentioned most of these topics already. We'll just go a little bit deeper into each of those. Alas, I don't have time in just 1 hour to go into details of all the features in intelligent query processing that we'll have in SQL Server 2022 and in Azure SQL Database. So I've chosen just a few highlights. But you'll hear me talking about all of these in further detail and even in short snackable YouTube videos. All right, so let's set the stage of where we are now with a brief history of intelligent database and how we got here and how you can get started. So you probably know this feature tree, and this is the intelligent query processing feature family. And you see there are a number of features that were enabled back in SQL Server 2017, and then we moved on to increasing the scope and the scenarios that we tackle in intelligent query processing in SQL Server 2019. And as you would expect, Azure SQL Database saw most of these improvements ahead of SQL Server 2019 and 17. Now, the principles that are guiding our intelligent query processing roadmap, if you will, are three simple principles. One, all the features need to be, or most of the features need to be available by default, just by flipping to the latest compatibility level. So no code changes there. They need to deliver broad impact. They need to be really successful in improving the scalability and performance of your workloads with minimum implementation effort. And I say minimum here because, as you see on the screen there, there's actually an asterisk in approximate query processing. That's a family of new T-SQL functions that, to be able to use them, you have to change your code. But apart from those new T-SQL functions, all the features you see on the screen here, you just get yourselves into the appropriate database compatibility level, and they just work for you. And the intent is that critical parallel workloads should improve, just running at scale, while remaining adaptive to data changes and data distribution changes occurring in the underlying tables. These three principles have not changed now that we're going to SQL 2022. If you want to know more about all these features, you have those short URLs there. You even have demos and self-guided notebooks in that IQP demos URL there, so feel free to grab them. Now moving on to SQL Server 2022. And again, this comes hand in hand with Azure SQL Database. You see that there's a number of new features there, or feature extensions in some cases, regarding SQL Server 2022. I'm not going to discuss all of them in this session today, as you've seen in the agenda. I'm going to talk about C feedback, DOP feedback, parameter sensitive plan optimization, and the feedback persistence and other improvements to memory grant feedback. Approximate percentile is also, as Bob has mentioned briefly, is also being added to the approximate query processing feature family. And we have a different feature called compilation replay that will be able to tackle the so-called compile storms when we have a number of a very busy server that has thousands of plans in the cache. And for example, you have a failover and the new workload starts connecting in, and you suddenly have a compile storm of new compilations coming in, and we want to be able to alleviate those high-end scenarios. But as I mentioned, so this is the new features coming in to this family tree. So without further ado, let's move on to the drilling down to each of these. But first, the basis of most of these features is the query store. The query store that we've introduced back in SQL 2016, that we've dubbed the flight recorder of your workloads is front and center in this release and in the next wave of intelligent query processing feature family. So we start with Query Store on by default. We are taking the step of turning on Query Store on by default for new databases only. And the reason is simple. As we introduce new features and new configurations for databases, if you take a database from an older system and either restore or attach to a higher version engine, we typically don't change any database options. And Query Store being on is one of them. Why are we doing this now after these several releases of SQL Server? Well, throughout the years and even in Azure, we've added numerous scalability improvements around self-healing, around self-throttling, around optimization of latch mechanisms. So this is the summit of all those scalability improvements coming to fruition, and having the confidence that we are at the place that we can turn this on by default. We also have much better standards, much better defaults, starting with SQL 2019, which are the same as Azure. So for example, the fact that the capture policy is now default auto instead of being all, that's one fundamental difference, but there are others, like the size of the query store. The intent of these improvements that we've pushed throughout the years, and a few new ones that were only in Azure and are coming to SQL 22, is the ability to handle heavy ad hoc workloads, which has been somewhat of an Achilles heel for past versions of SQL Server. And we'll be able to better handle heavy ad hoc workloads due to some internal memory limits and throttling that we've put in place. So that, coupled with the custom capture policies that we also introduced back in SQL Server 2019, which are available for you to fine-tune if needed, those capture policies, all of those gives us great confidence that we can turn this on by default. And so by turning this on by default, we also enable a number of new scenarios. For example, Query Store hints. Query Store hints, which are now in public preview in Azure SQL Database, are already in CTP 1.0 of SQL 2022. And by the way, throughout the session, you'll see with each or most of the features that I'll introduce, a feedback email at such point where you have access to the feature, either in Azure or in SQL Server, and you have feedback, feel free to use those emails to reach directly back to the team to provide feedback. All right, so let's set the stage here of what are query hints. We know that ideally the query optimizer should have an optimal or good enough query plan for each query execution. However, sometimes this doesn't happen. And there are several ways the developer or DBA can go around it, and they can rewrite the query, obviously, but some of the most quick actions that someone can take is to hint the query to, let's say, shepherd the optimizer to go through a different path and produce a specific type of plan. These hints are specified by the option clause that you see on the query on the bottom of the screen there. And they will be used to influence or shepherd, like I mentioned, the behavior of the optimizer to choose the determinate paths to produce a plan. So you see on the screen there, for example, I'm using a hint to disallow batch mode and to also force recompilation on every statement. That's just a couple of examples. Now, because query hints, especially these types of query hints, are very important, especially to troubleshoot or to do point-in-time query tuning without actually having to likely refactor the entire query. Applying this today allows DBAs and developers to provide those localized solutions to fix those performance-related issues. However, in many places, you can't really go and rewrite the query, rewrite the original query text. It's either in the application layer, or obviously there's quite a high bar to go and rewrite queries that run in production. So DBAs can't often go and do these changes. Either the T-SQL is hard-coded into the application, then it may even be generated by the application through some ORM, so it's often difficult to go and hint queries. And plan guides were available. They've been available for some versions now, but the common feedback is that those are cumbersome to use, to implement, and even to manage. So we've heard you loud and clear. And it's because of that we're introducing Query Store hints. So this feature aims at providing a much simpler method for you to identify a query and shape that query plan through query hints that you need to play with without changing the application code. So this obviously leverages query store, as the name indicates, which is on by default in Azure SQL database, and it will be on by default for new databases in SQL 2022. So this will greatly improve the experience of tuning based on query hints. Here's how we can use it. First step, find the query in the query store that you want to modify. So this is an example of a query that I could go into. I can go into the sys query store query text, joining with the sys query store query to get the ID of the query that I'm looking for, and I get the query ID there. For the text, I'm using there a subset of the text that I know is in the query that I'm looking for. And I get the query ID 46006. Okay, I just take that and I'll use the store procedure SP query store set hints with the query ID and a string made up of all the hints I wish to apply on that given query ID. And so in this case, I'm applying option #. But I can apply multiple hints. For example, in this case, I'm reapplying on the same query ID option recompile, max UP1, for example, and even forcing the query optimizer compatibility level to come down to level 120. So like that influences how the plan will be generated. If at a later point I choose to change the hints that are applicable to this query ID, either remove some, add more, completely change what they are, I will always need to invoke the store procedure with the same query ID and use the parameter of the entire set of hints that I want to use for that query. So they are always overwriting whenever you execute this again. To remove a hint, also very simple. You can just use the SP query store clear hints, pass the query ID, and all the hints are gone. So there will be a recompilation, and a new plan will be created for that specific query. About the scope and behavior. So as you probably noticed by now, query store hints supports at this moment query level hints only. The query store hints will be persisted as the query store. That's what the query store is there for. So they will survive restarts. They can override hard-coded statement level hints and plan guy hints. So if you issue a hint in the query store over a query that had, for example, a statement level hint already hard-coded, your hint, if it's not incompatible, will supersede the one that was there, hard-coded in the query text. And like you see in the bottom of the screen there, if there's a contradiction, if the queries that you are now using versus the ones that exist are come up with an impossible scenario, then will not block query execution. The query store hint will not be applied and will still allow the query to go forward. Right, another improvement on query store is about secondary replicas. And you notice that I'm kind of rushing here because there's a lot to cover in 1 hour, and I really want to get you this content and this level of insight for now. So query store for secondary replicas has been one of the highest requested features since query store's inception. It will be in public preview next calendar year in Azure SQL Database and in an upcoming CDB of SQL Server 2022. Again, the customary email, like I mentioned there, for feedback once we have the feature and you can start testing that. How does this work? So the intent is for you to get the same support you get on the primary, you'll get on the secondary replicas. So you have read-write workload running, and that's running against the primary replica, and that information is captured by the query store. Before, when you were running your read-only workloads against secondary replicas, there was no specific information being captured by the query store, so there was no way for you to neither analyze nor act upon specific scenarios that you would see only on secondaries, only on read-only workloads. But now we're changing that. So the read-only workloads that run on your secondary replicas will be available in the query store that resides on the primary. So we'll be using the link that's established by always-on availability groups to transport the information back to the primary replica and persist it properly identified as coming from a secondary replica in the query store. So the query data will be visible either by the role type, meaning that it's a primary or a secondary, or by name. You can look at query store information on workload that ran in a specific replica name. How do you enable this for secondary replicas? Well, you need to do most of the work in the primary replica. First of all, as you probably would notice, you need to set the query store on, and that's done in the primary replica because that's where the query store sits. To turn on the query store support for secondaries, you still need to execute this on the primary because as it happens with every other execution of any DDL or the DML that's done on the primary, it will be replicated through the always on availability group link to the secondary replicas. Will enable the support for secondaries with this command, alter database for secondary set query store on. Okay, so that's how you set it up for the secondary. And then you need to check the state. Is it on? Is it working? Well, we have this catalog table here, database query store options, and you can look for, you can query that table, and you need to look for two things. The desired state and the actual state is equal to 2. That means that it's on and it's read-write, and they're both the same. And or the read-only reason is equals to wait, meaning that you're running this in the secondary replica, and that's the scope that you are executing this on. Forced and unforced plan, as you would expect, works with on secondaries. So you'll be able to force a plan and therefore also unforce a plan specifically on secondary replicas. As you see on the screen there, you're still using SP query store forced plan and unforced plan. We are adding a third parameter. So the first is query ID. The second one has to do with the plan ID. And the third one, as you'll see the description there, is the scope parameter. The default is 0, meaning that if you have scripts right now that are using SP query store forced plan and you move to SQL 22 or to Azure, you don't need to add a third parameter. The behavior will be the same in the sense that if you force, if you use this without this parameter, you are just forcing on the read-write replica, so the primary replica. However, you can see that you can force on all read-only replicas, or you can force and then force in all replicas, including the read-write. Okay. As for maintenance, well, SP query store flush DB, you'll actually see me using that in a few demos today. That's what you use to flush the in-memory information of query store to the on-disk structures. So this will apply only to the replicas where it is executed. So if you run on the primary, it only affects the primary. If you run on the secondary, it will only affect on the secondary. And what it will do is that will enqueue all the in-memory data to be sent back to the primary. So you see there other store procedures like to remove plan or to remove a query or to reset execution stats. Those work per replica set. So when you add those, you are affecting the entire replica set, be that the primary and the secondary. So it's an and condition. All right, let's move on to the features in intelligent query processing that some of them, as Bob mentioned in his session about an hour ago, are built upon or are predicated upon query store being present, because that's they come joined by the hip. So parameter sensitive plan optimization. This will be in public preview in Azure SQL Database at the beginning of calendar year 2022, and it's already in SQL Server 2022 CDP1. Again, the customary feedback email there. So let's define the problem first. Parameter sensitive plans, or as they're commonly called, parameter sniffing issues, because we're talking about the problem state here when we're talking about this scenario, is where we can have, or traditionally, and until now, we can only have one cached plan for a given parameterized query. And that single plan may not be optimal for all possible incoming parameter values. If we architect our system correctly, and then from an application perspective, we can mitigate by, for example, making sure that at least that plan is optimized for most of the executions, but it will never be possibly optimal for all incoming parameters. So if the first compilation that comes through the gate is not representative of most executions, that's when you hit the problem state. That's when you have a perceived bad plan. Oh, this is using a scan, but usually uses a seek. What happened here? Well, the first parameter that they executed was not the one that's most representative. So that's what you got there. You still got a good plan, but a good plan for a very subset, a very small subset of your data distribution. So let's see this just visually first before I go to a demo. Parameter sensitive plans today, how do they work? Think of an example of a database that has real estate agents and their properties, their property portfolio listed in a table there. And there's a store procedure that I compile with an agent ID. And once I input that agent ID, it gives me back a list of all the properties that that agent has in the portfolio. So if I have a new compilation, net new compilation of this store procedure, that's after the restart or after the database came online, whatever, I compile with agent ID 4. I get a plan that's optimized for that agent ID 4. I see there that I return 3 rows because that agent only has 3 properties in the portfolio. And the query time stats, it doesn't even register 1 millisecond, so I see that's rounded to 0 there. CPU time and elapsed time, so very, very fast plan. Now, remember that at this point, the query plan is compiled, it's in the cache, and the query is parameterized, so every new parameter will reuse the same plan based on a seek, a key lookup, and a nested loops. When I use that same cached plan for agent ID 2, well, agent ID 2 has, as you see there, almost 5 million rows in the database. That means that I'm still using the same plan. I have the index seek, the key lookup, but I'm doing 5 million index seeks, 5 million key lookups. And then I'm using a nested loops to join this, which is highly inefficient. And then I'm still having to do a sort on top, which, as you see by the warning sign there, is actually in this first execution spilling. If I haven't said this before, all the intelligent query processing features can work together to improve workloads. So in the second execution of this scenario, because I already have memory run feedback here, this part would be resolved, the part of spilling to this. Anyway, back to the scope. I see the query time stats there. I'm using almost 1.5 minutes of CPU, and I'm using almost 4 minutes of 3.5 minutes, roughly speaking, of elapsed time. This is clearly not a good enough plan for this parameter. And I also see that by the very large difference between the number of actual rows and estimated rows. Estimated because they were estimated for the first parameter execution. Now, if I recompile that for agent ID 2, if I use the option recompile the store procedure, and it happens to be the first execution, then I have, as you see, that a much better plan. I'm doing a cluster next scan. The cardinality estimations are right on the money, so the plan is much more efficient for this scenario. And you see that's reflected on the runtime and CPU time, almost dropping to 50%. This is the problem that you have today. And today you can solve it in a number of different ways. You have a number of workarounds. I mentioned recompile just now, but you can, for example, if you know beforehand what is the most prevalent parameter that you are using, you can use an optimize for, option optimize for hint. And you have a number of other possible workarounds on the screen here. Each of them has their pros and cons, so your mileage may vary when you use each of these options. Enters ESP optimization. ESP optimization is our attempt to go and start solving this problem space. It's enabled by default using dbcompat 160. And what it does is it will automatically enable multiple active, I stress again, multiple active cached plans for a single parameterized statement. So in essence, that agent ID 4 and agent ID 2 would have 2 different plans cached, and depending on the incoming parameter, they would execute independently. So the cached execution plans will accommodate different data sizes, and those are based on the parameters that you present to the parameterized query. So we'll use those runtime parameter values to go and look on the underlying statistics to find what are the most at-risk predicates, and then we'll use those. Now, I just pause here to share with you some of the design considerations we had with this feature. One, and I've heard this on the FAQ today or the Q&A today in Bob's session. How do you prevent cache bloating? Because we know that with this feature, probably we can generate too many plans, would create cache bloat, replacing one problem by another. We don't want that. So we do limit the number of plans in the cache. And by the way, we also limit the number of plans that can be in the query store per each of the PSP optimized plans. So another design principle is that the overhead of using PSP optimization, that you'll see some details in the following slides, should not outweigh the benefit it provides. And the benefit can be conceptually understood just by the visual example I provided in the last couple slides. And it needs to be compatible with query store plan forcing. And I have a slide that I added on this later on. So what happens for predicate selection? So during the initial compilation of the parameterized query, we'll look at all the predicates that are in use, and we will look at the ones that are most at risk. Most at risk meaning the ones that have most widely variant data distributions associated with those predicates. Now, those predicates are, as you'd expect, column names. So we will look at the predicates based on the statistics that cover those columns. And we'll select up to 3 of all the possibly available predicates. If your parameterized query has 5, 6, 7, whatever number of parameters, we'll look at all of those and we'll choose it up to 3 most at risk. In this first version, we are targeting only equality predicates, as you see on the screen here, where agent ID equals a parameter. The reason we did this is we know from telemetry that this already covers a wide range of use cases. We're attacking, let's say, the 80% case, and then other scenarios will come in future versions. As I also mentioned, we are using the column statistics histograms to identify all those non-uniform distributions, and those will be the basis of determining, let's say, the buckets that we will be having, that we will define the data distribution and then find optimal plans to access that amount of data. There are 2 important concepts to keep in mind with ESP optimization. One is the dispatchers, the other one is the query variants. Let's drill down on what these are. So a dispatcher plan, so when you execute the first time a parameterized query, will create something called a dispatcher plan. This is a structure that contains the logic, and that logic is called a dispatcher expression. And that logic is what defines the buckets of data distributions that we found for that given predicate or set of predicates. That dispatcher plan then maps to 1 or more query variants. That means 1 or more plans for each of those buckets that we identified that will likely require different strategies to access that data. So those will be the cardinality range boundary values. The dispatcher plan is built on the first optimizations, on the first compilation, and it's built along with the first variant, because obviously you need to execute the plan. So the first variant that was identified needs to be compiled immediately, and that plan needs to be available. The dispatcher also determines the available scope for all the predicates that were identified. So in other words, when we create a dispatcher plan and we create the first variant, we don't create the other possible variants. We don't compile the other possible plans. Those are pre-identified in terms of boundaries in the dispatcher plan expression, but are not compiled. So that overhead does not exist. We may never even build them if there's no such parameter ever executed that would activate those specific boundary values. The dispatcher plans can be individually or can be independently rebuilt if there are significant data distribution changes. For example, you are joining among several tables and you have predicates among several tables. The data in 1 or 2 tables changes dramatically in the sense that a predicate that was not considered at risk is now at very high risk. We will recompile the dispatcher plan and probably will bring in that new parameter, at-risk parameter, into the dispatcher expression, and that may change the entire context of execution, because now the PSP plan is being optimized for a different set of predicates. Okay, so moving on to query variants. Each query variant is a plan, and therefore it has its own query execution plan ID in the query store. And the query variants, as you saw also in Bob's demo, they will have the same query hash value, but each of the variants will have a different query plan hash value. So you'll be able to map a single query to the possible variants that exist through comparing these two values. plan, and like it happens with the dispatchers, the plans for a variant can also independently recompile as needed. And that's the same recompilation thresholds as any plan with or without PSP. So that nothing changes in that perspective. To give you more of a visual aid of these boundaries and what these mean, let's look back at the parameterized query that is that the search for agents portfolio. And a dispatcher plan is produced. And the dispatcher expression identifies three possible boundary values that would result in three different plan choices. So we have a variant that we identified when agents have less than 10,000 listings, and we see a seek and a lookup and a small memory grant is good enough. But on the other extreme, we have query variant for agents that have more than 1 million listings, and we saw one case of that. And the plan should be actually a scan and provide a large enough memory grant to be able to accommodate that operation. So this is just a visual representation of how this feature is working. We compiled the dispatcher plan first, but we only compile the variant that's being executed at the moment. For example, if I never execute a parameter that would yield between 10,000 and 1 million listings in the middle of the tree there, that variant would never be compiled. So we don't preemptively compile query plan variants. All right, let's do the time check. We have half hour, so I have time for this demo here. And to look at some of the details that you have available in the query plan to allow you to see some of these choices. All right, so I'm using the property MLS database, which is exactly that scenario of having multiple real estate agents and multiple properties available in the portfolio. I'm setting the DB compat to 160. Let me put this a little bit bigger. DB compat 160, the query store is turned on, as you would expect. I'm using rather aggressive settings here, so never mind them. And I will be clearing the query store, so just doing some housekeeping here. Let's look at the store procedure property search by agent. So it is a rather simple store procedure. It takes the agent ID. It takes the agent ID parameter, and then it selects from the property table where that equality predicate matches. So agent ID equals the parameter, and it's doing an order by listing price. So fairly simple query in here. So the first compilation of this store procedure would look on the statistics that are tied to that predicate. So where agent ID equals agent ID, so the column agent ID on the property table. I've pre-identified which stats that is. So let's look at the histogram for that stat. And you see here that I see immediately that for range IQ 1, so for agent ID 1, I have roughly 5 million rows, so 5 million properties. For agent ID 2, the same thing. And then I have between a few units and I have a few here with a few dozen properties. So very differentiated data distribution. This, by doing this analysis, this is how we build the query dispatcher expression and are able to determine the buckets of possible query values. So what I'll do first is I'll execute property search by agent with agent ID 2, which I know now that it will return roughly 5 million rows. I don't want to waste your time, so I've done that before. And as you see here, I get a plan that's the clustered index scan, the sort, which was the first execution, and that's basically the plan that we saw before. So this is highly optimized, given the current indexes that exist on the table, for this to return this large number of rows. What happens when I execute with agents that have very few properties, like agent ID 4 and agent ID 8, for example? So let's pull those executions. And I see the execution is really, really fast. And if I look at the execution plan, it is rather different from the one I executed with property agent ID 2. Now you're telling me, okay, but are those two active plans? Let's look at that. We can look at the sysdm exec cached plans, and I'm doing a partial search here by the text. And I see that, yes, I've executed this plan handle which has this query text. It's exactly these 6 executions here of agent ID 4 and 8. and I have one execution of the other parameter, which was the single execution of agent ID 2. So I do have that in the cache. Looking at the plan properties, let me look here. Oh, come on, just help me a little bit. Properties, there we go. You'll see that once you get access, these are, for now in this early version, those aren't defined here. So we need to go and look at the actual show plan execution XML to look at the new properties that are available. And the first one is this dispatcher element here. This dispatcher element, as you see, has information about what decisions were made by the feature in order to create these different variants. So I have a low boundary of 100. I have a high boundary of 1,000,000. So here I see the high and low boundaries of the buckets that this was used. I see the statistic that was used to come up with this calculation, and I see when it was last updated. I also see information such as what was the column and the parameter that was used. In the query plan element, I also have one additional information, which is the query variant ID. So I use the query variant ID 3. At the moment, there are no other query variants. There's only one other query variant, I'm sorry, in the plan cache that belongs to the other plans. And I could easily look at them just by doing this. And if I go and look at the execution plan and do this, I see here in the query plan element that this was query variant ID 1. So there you have it. You have two cached plans, different query variant IDs, same dispatcher plan for different incoming execution types. All right, let's go back to the presentation. How to force and unforced plans. This was something that came up in Bob's session chat. So same forced and unforced plan procedures. So they work the same way. A few considerations here, because now you have additional layer of complexity based on the fact that you have dispatchers and you have variants. If you force a variant, its parent dispatcher is not forced. So you can force variants across the board for different queries, and we will respect that. So that's what you're setting. However, if we need to recalculate the dispatcher, or if a different dispatcher is forced, let's say you force a different dispatcher, that means that you are setting now a different, let's say, scope for the available plans. I did mention briefly that if data distribution changes significantly and suddenly a predicate that was not considered at risk is now considered at risk and it's brought into the fold, then the dispatcher will accommodate for that. That creates a new execution context. So therefore, the table has changed, if you will. So previously forced variants in the same dispatcher will be forced again because they'll retain the state. And if you have variants that were not forced, those are the ones that are available for the scope of execution of that parameterized statement. Previously forced variants in other dispatchers, they will become inactive. Now, they'll still keep the forced state, but they will not be actually used. They will keep the forced state because at some point in time, you want to force back a previous dispatcher. You can do so, and that automatically reactivates the child variants that you had previously forced as well. So that hierarchy exists here. All right. Moving on to a different feature, memory grant feedback, the feature that you know, but we've added two main improvements here. The ability to persist data, but also the ability to be smoother, more intentful in how we calculate the progression of the memory grant. This will be in public preview in 2022 in Azure SQL Database, and it will be in an upcoming CTP for SQL Server 2022. Let's set the stage here, memory grant feedback. So you probably encountered this issue before. You have queries that either spill to disk, take too much memory, and that, or take too much memory, and that happens because of poor cardinality estimations. It's based on the cardinality estimations that the memory that would be optimal for that given plan to execute is calculated. However, if we misestimate memory, we don't have enough memory for a query to execute. And in the case of hash operations or sorts, we will spill to tempdb. That is an inefficiency. But the other extreme is possible. We may overestimate memory, which means that you are grabbing memory that we won't use, but it remains allocated for that query context until end of execution, which means that you are not able to run more concurrent queries because memory is taken, although it's not used. So it hurts concurrency. And what memory grant feedback does is it can remove spills, it can improve concurrency for those repeating queries. So this is something you know today if you're using SQL Server 2017 or 19 or Azure SQL Database. You just need to be in the right compatibility level. So this memory grant feedback applies to batch mode queries in dbcompat 140. We expanded to include row mode queries in dbcompat 150. So you don't even need to be in dbcompat 160 to use the new features. You just need to be using memory grant feedback. So two improvements, as I mentioned here. One is persistence, because one problem that you face is if you evict the caches, either because the plan aged out or because there was a failover, for example, the feedback is not persistent. And so if the plan is evicted and then you execute that again, there's no record of how a previous learning process occurred. There's no record of what was the optimal memory grant before. So we need to relearn, and that may take a few executions to get to the proper place. The solution is to persist that feedback, persist it in the query store. So by persisting in the query store, it survives restarts, it survives failovers. So as long as nothing changed in terms of the obviously plan being recompiled and you getting a new one, then that memory grant feedback is reapplied to the new execution. The other improvement has to do with fixing oscillation. So memory grant feedback will adjust memory, the current version of memory grant feedback, based on always on the last execution feedback. And so it looks at the last execution feedback and takes that as the most correct, and it will use that for a subsequent execution. However, for example, if you have parameter-sensitive queries like the one I showed before in the PSP optimization, if you didn't have PSP optimization, obviously, the point would be that sometimes you're taking in just 3 or 4 rows, very small memory grant, but sometimes you need to bring in 5 million rows, which leads to all sorts of issues like spills, which is precisely because of memory misestimation, which may lead to an oscillation pattern like you see on the screen here, where the grant size is always falling one step behind of the actual memory that's needed. And for the current version of memory grant feedback, we actually just, after a number of executions, we just tap out and say, sorry, we can't really reach a point where we have a stable memory grant, so you need to take care of this yourself. We can't apply this automation anymore. And taking care of this yourself, by the way, would mean that you find the sweet spot and you probably will use the max grant percent hint, probably even with query store hinting to be able to support that. But what we're doing is that we're fixing the ability to react to that oscillation scenario by smoothing out the grant size based on all the past execution usage history. So the optimization here is to try to minimize spills more so than trying to correct for overestimation. And this is using a percentile-based calculation here. Visually speaking, you can see on the screen there that you see that after some time, the percentile granted is smoothed out. That's the blue line there, even though the requirements keep changing in terms of the last use granted and the actual needed number. We'll account for all the previous executions rather than just the last one, which means that we can actually keep adjusting over time without having to give up at a certain point. That's the major improvement here. Yeah, so I'm skipping the demo for this, given that we're in the time crunch. Let's move on to the next topic.
Actually, Pedro, just to let you know, you're to 12:15, so if that and not 12.
Oh.
Yeah, so that's bonus. Yeah.
Then I'll do the demo here. Thank you, Joe. I wasn't looking at the chat window.
No worries.
All right. So please work with me. And of course, my VM had to hang or something like that. There we go. Let's come back to life. Good. So let me push this away. And I don't need this as well. And I also don't need this. Let me bring in the demo for, here we go. Okay, so for this, I'm using the Wide World Importers DW database. I'm actually going to set DB compared to 150. It's a choice. Again, setting the query store to on because I want to use persistence, even though I'm not going to reboot my instance to show you that it persisted. But once you get to play with this, you'll see. And it froze again. There we go. And I'm going to clear the query store. Just want to make sure that the query store, procedure cache, everything is clean. And I'm going to use this store procedure that will force a row underestimate. So this store procedure will look at a couple of look at the fact table, dimension table, and it's trying to derive a lineage key out of this this data set here. So what I'm going to do is compile. This has a huge lag here. Okay. I'm going to alternate the execution of these queries, of this store procedure, based on a parameter that I know doesn't have any rows, parameters that have some amount of rows and that would impact memory grant size and runtime. And I will do this alternating as soon as this allows me to. There we go. I'm having a huge lag in my access. This is not great. Internet provider, do not fail me now. Okay. So I have here executions of. This is not helping. There we go. Just one more. One more. There we go. So as this come in, you see that the first three executions didn't yield any rows, so we'll probably have a very low memory grant. And then you'll see that upcoming plans will have larger memory grants. There we go. This one returned quite a few rows. I'm not looking at the execution plan, which is something that I wanted to do. So let me stop here, do this. There we go. And execute this again. So plan for the one that really brings in no rows, very simple plan here. If I look at the properties for this plan and I go to the memory grant information, I see that it's already percentile adjusting based on the fact that I'm running executions that have widely variant number of rows coming in, widely variant data distributions underneath. And so instead of going to a place after a while that the feature just disengages, just gives up, we actually see here that it will keep adjusting as new incoming executions come in until it reaches a stable point, which may take longer than in the previous version because we were just looking at the previous execution, and now we're smoothing out based on the percentile. This, as you see here, is the new value available in the show plan XML that will allow you to see what is the current state of memory grant feedback and whether its percentile adjustment has kicked in or not. So let me go back to what I was. There we go. So C feedback. C stands for cardinality estimation. And the cardinality estimation process today is, the cardinality estimation is the process by which the optimizer will know or will estimate the number of rows that will flow through a plan in all its operators. And with that, be able to not only find the more appropriate operators based on the estimations, but also come up, for example, with the memory grants like we just see. The cardinality estimation process is based on a number of models. And those models carry some assumptions about data distribution, about how data exists in the tables and views that you are accessing, and also about the expected usage of the data and how the table is queried. So this session is not about cardinality estimation per se. So if you want to know more, you have that short URL there that you can go and read our thorough documentation on cardinality estimation. One point I want to make here is that the cardinality estimation process sometimes makes incorrect assumptions. Those will lead to poor plan quality, and something needs to be corrected. What we've learned is that one model really does not fit all scenarios. And if you have been working with SQL Server for some time, you probably remember that back in SQL Server 2014, we changed some of the fundamental cardinality estimation assumptions and some of these model changes. So C feedback is our attempt to automatically correct those states so that you don't need to be a cardinality estimation expert in identifying those small signals and sometimes big signals and how to go and correct them. The idea of C feedback is to look on the cardinality estimation model assumptions that are in use, and I'll give some more detail on that are in use over time, and then apply the most historically correct assumption. Correct based on actual experimentation, based on your feedback, on the feedback over your workload. So the C feedback feature will identify in certain query patterns that I'll discuss next, model-related assumptions that may be at play. And it will evaluate whether those are accurate enough as you execute more of that specific query. So this is, again, like MGF and like other features, just for repeating workloads. If an assumption looks incorrect, then we'll test a different cardinality estimation model assumption and verify if it helps. We'll verify it, again, based on the executions that your own application is sending in. And if it helps, we'll actually replace the currently cached plan with one that is hinted in a way that overcomes that inefficiency that we found. And we'll be addressing three main scenarios in this V1. These three main scenarios were selected because, historically speaking, by our experience, are the scenarios that most impact upgrades, especially coming from very old versions of SQL Engine, like 2008, 2012, all the way to Azure or to newer versions of SQL Server. And we want to reduce that upgrade friction based on the so-called, air quotes, old C and new C. The idea is that you should not have to be an expert on cardinality estimation. You shouldn't have to care about concepts like independence and correlation and row goal. We're just geeking out here, but you shouldn't have to worry about that. We also know, by the way, that there's no single set of models and assumptions that work everywhere. So this is not a new CE, by the way. I just want to make that very, very clear. And what we're doing here is that for those repeating queries that are in the cache, we'll adjust the models based on use hints. So we'll piggyback on the hint support that is being introduced for the query store to influence through query hinting the outcome of the optimizer choices to produce a plan that should be better than the defaults that we were working with for that given plan. We will still honor any hard-coded query hints that if they're used. You may ask here, hang on, but you mentioned a while ago that query store hints can supersede hard-coded hints, and now you're telling me that you'll honor hard-coded hints? Well, the principle is the same, is that you are the user, you are in control, you should know what you're doing. So if you, as a user, use the query store hint, that will supersede any hard-coded hint inside the query text, for example. However, if a automated feature like C feedback finds the need to tweak a query through hinting, and you have hard-coded hints that conflict, then we'll back off. We won't do anything. And that's the same principle, is that the user has priority. And like I mentioned, only verified feedback is persisted. What does this mean? So as I said, we piggyback on the next execution sent by the application to verify whether the change in the model yielded a better result or not. If the next execution regresses, meaning it takes longer time to execute, for example, we take that as a regression, we back off. So we won't work on that query again. If you cancel the query, let's say in hindsight, the query starts taking longer and you as a DBA go in, kill the session, roll back the query. A canceled query is also taken as a regression, which means that the feature will back off and we will not touch that query again. So I just wanted to make that clear because it's important that we have these built-in safeguard measures. I'll look at one demo for this scenario, which is, but no, I don't want to say changes. And for this, I'm using the AdventureWorks 2016. I need to set the Bcompat level to 160. And I'm setting query store on. As you see here, I am also clearing the query store, procedure cache, all the usual housekeeping. And one thing that I haven't mentioned before, but it's important to mention, is that the force last good plan feature from automatic tuning is still, for all the features we've seen today, is still the backstop for any regression. So while we have built-in safeguards in all of these features to back off, to do no harm, we don't control all situations, or we don't know all situations that have not happened yet. So we still have APRC, so force last good plan, as a backstop, ultimate backstop to catch regressions and fix them through plan force. Okay, so having said that, that's why I always enable force last good plan. Let me set up a X event capture, and this X event capture is using two events: query feedback analysis and query feedback validation. Query feedback analysis fires when a query comes through the gate. It's executed enough times. It is of a pattern that we identify that matches the row goal, or correlation analysis, or joint containment analysis. And the other one is validation. Once a query is validated, either it's successful or not, it goes through that gate. And then if it was successfully validated, we persist the respective hint in the query store. And if it was not successful, as I said, we just back off. So let me start that X event session. And I want to look at live data. All right, can I bump this up a little bit? If I can, I don't know how, so I'll just use Zoom it. Okay, so I'll run this query 15 times. And for now, this is just a number that we're not documented. We may change this. This is just for the preview, but it gets a query through the gate. And the query that I'm using here, look that it has a top keyword. Using a top keyword is one of the several patterns that we know will trigger the engine to use the row goal optimization. Now, as I mentioned, optimization, it is an optimization, but sometimes it doesn't work well. So we'll be able to identify poor use cases of row goal and correct for those automatically. So I executed 15 times. I'm going to do this for the next execution. I'm going to flush the query store, because this all needs to be in the query store to kick the analysis. And one thing I'm going to show you is that the plans are indeed in cache, and some interesting data on this. So I have 15 executions of my compiled plan, and I can see here that it's indeed my query. And if I look at the query plan, I see that it's using a clustered index, two clustered index scans and a merge join. Okay, so let's keep this in mind. Let's go back here, and I'll execute one additional time. And this should, it's a live demo, hopefully it's working. This should trigger query feedback analysis. Now, what we have here, I'll zoom in for you to have more context. So the query feedback analysis is fired when the first time a query gets through the eligibility gate and gets analyzed. So in this case, it identified that the optimizer row goal strategy is at play in this plan. And it says, you know what? This doesn't look like it's based on internal metrics. It's not, it's probably not a good use of optimizer row goal. Let's use the next execution with this use hint, which, by the way, all the use hints that we use in this feature are thoroughly documented. If you go to the query hints documentation, they're all there. So in this case, we'll be disabling the optimizer row goal in the next execution and see if it works. What have I done? Okay. There we go. All right. So let's look at the next execution, and the next execution should trigger the another event. And there we go. So the other event was the feedback validation. So what we see here is that the original CPU time was almost 29 seconds. And by disabling row goal, I was actually able to get the plan to execute in only 16 seconds. So I have a standard deviation CPU time of over 5 seconds, which is very sizable. If I look at the plan now, I see that I have a radically different plan. I have the same two cluster, the cluster index scan. Now I'm using another index, and I'm using a hash match. And I was able to save, remember that this is for repeating queries. So just with this change, I'm able to save a lot of CPU, and I'm able to actually increase concurrency, and I automatically tuned to this effect. I tuned this query. Okay, let's go back to the deck, and let's look at the last feature of the day, DOP feedback. DOP stands for degree of parallelism, and this will be in public preview also in the calendar year 2022 in Azure SQL Database, and it will be in an upcoming CTP for SQL Server 2022. Customary feedback email there once you get access to the feature and you start using it if you have feedback. Now let's set the scope of what we have as a parallelism today. Parallelism is often a very beneficial feature or method of execution, if you will, for reporting queries, for analytical queries, for otherwise for any query that moves and processes large amounts of data. Parallelism is efficient or is more effective. OLTP-centric queries, however, sometimes may be eligible for parallelism, but more often than not, they could suffer from parallelism inefficiency. What do I mean by that? Well, if the engine has to spend more time coordinating all the different threads, and that time outweighs the efficiency of running that query in parallel, meaning, in other words, if I would execute in serial, it would be more efficient than running in parallel. That's what we're trying to address here, is when parallelism is efficient for any given query. So before SQL 2019, by the way, the default value for max DOP was 0 in SQL Server. That meant if the query is eligible for parallelism, if it goes above the cost threshold for parallelism, then use all available schedulers at the moment of execution, and execute based on that number of schedulers. With SQL Server 2019, at setup time, we actually changed the default from 0 to a calculation based on the number of processors in the host that you are installing on. And we also changed, by the way, the default in Azure SQL Database to be 8. That's the DB scope configuration for max DOP. Okay, so enters DOP feedback. What is the intent of DOP feedback? Is to identify those parallelism inefficiencies for repeating queries. Again, this is for repeating queries. And this is based on looking at CPU time, elapsed time, and parallelism-related weights, and a few other latch types that have bearing on understanding whether parallelism was being used efficiently. And if parallelism is used in an inefficient fashion, then we will start lowering the DOP from its configured set, which depends on either the server level or database level DOP configuration. We'll start lowering it and observe its effect on parallelism efficiency. We'll keep dropping as we keep seeing efficiency increasing. So we'll verify if it indeed helps, but we'll never go from parallel to serial. So the minimum DOP we'll drop to is 2. Now, what happens is if we verify that lowering DOP helps, that verified feedback is persisted in the query store. It will survive restarts. And when the query is compiled again, if nothing else changed, then if it is indeed the same query plan through and through, it's the same query plan hash, then we will just reapply that DOP. One thing that's important to mention here is that the DOP feedback is not based on query store hints, as for example you saw with CE feedback, and that's because we need the feature to not recompile plans as we keep lowering the DOP. and a query store hint, as any hint would trigger a recompile. So the goal for this feature is to increase concurrency and reduce the weights around parallelism significantly, even if it slightly increases the elapsed time. And there's an inbuilt threshold that we'll keep iterating on throughout the preview, and that's why it'll be important to get customers to experiment on the feature and provide feedback. But we need to find a sweet spot between, yes, we've made parallelism so much more efficient, even though it runs slightly longer, but because we released so many resources, we are now able to run many more queries concurrently. The second point I mentioned is that DOP does not recompile plans, and that's important because we don't want to compound on a CPU issue by issuing recompiles. So this uses roughly the same methodology as memory grant feedback. So it's able to influence at runtime the allocation of resources, in this case schedulers, without recompilation. If we come to a point where we have stable feedback, we'll not stop there. Stable feedback will be, remember that this is for recurring workload. So stable feedback will be re-verified after each recompilation and on a schedule. And let's say if we find that we need to readjust DOP back up or even further down, we'll be able to do so. We will never go above the max DOP setting. That remains the ceiling. But the last known good value may not be good now because maybe you change data distribution and something in the plan is still the same shape, but it actually becomes more efficient or less efficient with the previously found parallelism value. So we'll adjust again. And another important thing is that we will upload max DOP hints. In other words, if you have a max DOP hint in your query, this feature won't even touch it, because the assumption is you wanted to set a specific max DOP. You don't want an automation to try to find the best available DOP for that query. So that's what we will uphold. Okay, so if you want to go further on all this, and there are other features, as you've seen, the 3 that I have not discussed yet, we'll do so in longer sessions. If you want to learn more about SQL 22, you have that aka.ms SQL Server 2022 URL there. If you want to participate in the EAP, if you have workloads that you want to try out many of these features, if you are serious about testing during this EAP private preview timeframe, if you later want to go to production as soon as we go GA, those are all great partnerships. So we'll welcome you. If you register through that short URL there, please be sure to be somewhat descriptive what we intend to test and what features do you intend to test. If we have more description, it will be much quicker to triage you through the list, and we have hundreds of requests already. If you haven't done so, please watch the technical deep dives on 22 in the SQL Server 22 mechanics that Bob has the first session there, and that really should help you get more acquainted with the overall investments in SQL 22. So thank you very much. You have my Twitter handle there if you want to shoot me some comment or have some question. And there's also the URL for the SQL Server team blog. And thank you very much for attending today. Hope this was useful.